Good morning. Today we are talking about integrated passive and wireless sensor for magnetic field, temperature, and humidity. The motivation of this work is that we want to develop a sensor that is passive, which gives ability of working without a battery, without maintenance, and can withstand harsh environment. And also wireless, which makes it able to remote accessible and easier installation. And also can fit applications that for the distributed sensing applications and sensor network applications. Yet, it is multifunctional. Here we're talking about magnetic field sensing, temperature, and humidity sensing. Here are some application examples. We think this kind of device can be used for the current line, overhead current line, transmission line monitoring applications, where the line current can be measured through the magnetic field measurement, and the temperature and humidity can also be monitored, where those sensing parameters provide very important information to maintain a high safety standard. Another application is to use for the traffic monitoring as well as parking sensors, because magnetic field can be used to detect the car, and the road condition can be monitored through the temperature and humidity measurement. Well, one thing I have mentioned that the passive and the wireless feature are of great interest for those applications because of the unlimited lifetime of the sensors and the remote access. Here's a short introduction. This sensor device is based on the surface acoustic wave technology. The SAW device, it converts the high frequency electrical signal into a mechanical wave. SAW device basically composed of two major components. First is an interdigital transducer called IDT, and another component is a piezoelectric substrate. The way it works is that when there's a high frequency electrical signal applied on these electrodes, it will accumulate charges in different polarity, and when these charges changes the polarity with a certain frequency that will induce a mechanical wave. This wave, also called relay wave, may travel along the substrate and get reflected by another IDT. Well, SAW devices have been widely used as resonators and filters for RF applications. Another important application is for wireless sensors. In terms of wireless sensor, there are two major types. First is the resonator type, basically is by measuring the resonant frequency of the device. Another type is the delay line type, which is by measuring the phase and amplitude change of the reflected SAW wave. And also in terms of sensing mechanism, we can sense the measurement through the intrinsic property of the substrate. It can be used for sensing the temperature and the stress, and also it can have a coating layer on the delay line, and also it can have a loaded impedance variable device connected with one of the IDTs. In this work, our device is based on a delay line type SAW sensor, and it utilizes all three sensing mechanisms. Here's the sensor design. Our sensor includes two delay lines. In the first delay path, we have R1, first reflector IDT, which is used for the humidity sensing, where we have a hydrogel coating between this area. And in the second delay line, we have R2, second reflector, for the temperature sensing, and third reflector for the magnetic field sensing. Here we have a magnetoimpedance sensor connected with the R3. So through the magnetic field change, we can modify the reflectivity of this IDT. And because the temperature not only influences the R2, also influences on all three reflectors. So this reflector not only used for the temperature sensing, but also used for compensation of the temperature compensation for the R1 and R3. Also, we have PDMS cavity used to cover the second delay path in order to isolate the humidity influence on the second delay line. Here we have antenna. Ideally, antenna can provide high-frequency electrical signals, and through the interrogator, we can achieve the wireless interrogation. This is the fabrication of the device. 4 major steps, starting with the fabrication of the IDT, with go and photolithography and dry etch to fabricate the IDT. After that, it's the e-beam evaporation, 3-layer structure for the magnetoimpedance sensor, and the mix-up process. And then we use hydrogel coated between these two IDTs, which is S1 and R1, and in the end, this PDM cavity is mounted on the second delay line. This is a fabricated device. As you can see, the size is about maybe smaller than 1 cm. As our sensor is capable of measuring 3 different parameters, we build a setup that can change all 3 parameters individually and simultaneously. Here you can see here's a chamber, and we have a gas in and out. And the gas is modified with different humidity level, which can be controlled by the pressure of a water pump inside the water bath. And the magnetic field is provided by a pair of Hamilton coil located on the two sides. And the temperature change is achieved through a theater cooler connected with a thermal conductor underneath the sensor. We also have a temperature reference sensor and humidity reference sensor to monitor the real change of the humidity and temperature. We use a network analyzer to interrogate the sensor through the RF cable, and the network analyzer can be used to measure the device's reflection coefficient through the vacuum parameters measurement. Here is the frequency spectrum from the network analyzer. You can see the working frequency has a bandwidth of 40 megahertz, and the central frequency is about 420 megahertz. After inverse Fourier transform, we obtain the time domain signal, where we can clearly see the three reflection signals from the R1 for humidity sensing, R2 from temperature sensing, and R3 for magnetic field sensing. The way we measure it is to extract the phase and amplitude of all three reflectors and changing the environmental conditions. This is our preliminary result from our first working device. Here, the picture I show here, the first red line represents the humidity signal from the sensor. The blue line represents the magnetic field signal, and the green line, the blue line represents the temperature signal, and the green line represents the magnetic field signal. And in the x-axis, the time axis, we divide it in 4 sections. In the first section, we change the humidity value, and the second section, we change the temperature only, and the third section, we change the magnetic field. In the fourth section, we change all 3 parameters at the same time. From the first three sections, we find that the sensor is able to work with individual changing conditions. We don't see a cross-off from the humidity and temperature, and the black line actually is a reference sensor. You can see that it fits quite well. However, we do see a cross-talk on the magnetic signal. It's mainly because the signal strength is comparatively smaller than the temperature and the humidity. But those noises, those interference can be compensated by the signal that we obtain from these 2 measurements. In the last combined test, we found that when the temperature is above a certain degree, the humidity component loses the ability to sense the humidity. And this is because of the hydrogel's lower critical solution temperature. In this hydrogel, we perform another experiment, gradually changing the temperature from 15 to 45 degrees. We found that below 27 degrees, the hydrogel is able to work. It is hydrophilic. And above this temperature, it loses its ability to contain the water, and it becomes hydrophobic. That means the sensor cannot work above this temperature. However, this can be improved by using another type of hydrogel, which can provide up to 65 degrees temperature. Another characteristic of the humidity component, although it has temperature constraints, we do observe a very large signal strength in terms of sensitivity. We have an overall 1,300 ppm change of the phase. Compared to the previous published result, it is quite impressive. Well, it is temperature dependent and nonlinear. That means calibration at different temperatures and humidity level is required for the sensor. Here's another calibration. Here's another measurement curve. We compare it with a reference sensor is from Honeywell, and we find that we only change actually 1% of the humidity level. We find that our device performs quite well, and it actually responds faster than the reference sensor, about 10 seconds. And in the end, we perform another measurement to demonstrate the wireless functionality. We use a pair of helical antennas, and we attach our sensor directly on a copper wire. And we apply different level of the currents, and our device is able to pick up the current change through the magnetic field measurement, obviously, and also the temperature change of the current wire. Although this antenna obviously works in the near field, which is just through the inductive coupling, but this somehow demonstrates this sensor's potential. As a conclusion, in this work, we developed a third sensor, a delay line sensor, with the capability of measuring the magnetic field, temperature, and humidity by measuring the amplitude and phase shift of the reflected signals. The temperature measurement fits very well with the reference temperature and has no interference from other measurements. The magnetic field measurement shows small interference, however, it can be compensated by the other two measurements. The hydrogel being used as a humidity sensing media shows a very large signal strength below the LCST. A hydrogel with higher LCST is required to improve the sensor's temperature range. The current measurement shows the sensor's capability of monitoring the current and temperature simultaneously, which somehow demonstrates the potential for the real-life applications. Thank you.